the murky silt off the coast of Charleston, South Carolina, lay a mystery that endured for over a century. When it was finally raised in 2000, it didn't look like a ship. It looked like a boiler, a rusted, riveted iron tube that seemed far too primitive to have changed the course of naval warfare. But on a freezing night in 1864, this crude vessel achieved the impossible. It became the first combat submarine in history to successfully sink an enemy warship. Yet the H.L. Hunley is not a story of triumph. It is a story of a weapon so inherently dangerous, it killed more of its own crew than the enemy. It sank 3 times. It claimed the lives of 21 Confederate sailors, including its own creator, Horace Hunley. For decades, historians believed the submarine was damaged by enemy fire or lost to a sudden storm. But modern forensic analysis suggests a darker reality, that the physics of its own weapon turned the submarine into an underwater crypt the moment it succeeded. This is the story of the H.L. Hunley and the engineering flaw that sealed its fate. We will dissect how it was designed and why it failed. To understand why engineers would construct such a volatile machine, we must first analyze the strategic map of the American coast in 1863. The Union Navy's Anaconda Plan was fully operational, a massive blockade effectively strangling the Confederacy's economy. The port of Charleston, South Carolina, the cradle of the rebellion, was the primary target. A ring of Union ironclads and wooden frigates sat anchored just outside the harbor, cutting off vital supplies and preventing the export of cotton. From a naval engineering perspective, the Confederacy faced an insurmountable problem. They lacked the heavy industry, the raw materials, and the shipyard capacity to build a conventional fleet that could challenge the Union Navy in open combat. They could not outbuild the North. Therefore, they had to outthink them. The strategic doctrine shifted from conventional engagement to asymmetric warfare. Confederate General P.G.T. Beauregard and the defenders of Charleston began looking for infernal machines, weapons that ignored the established rules of engagement. This environment of desperation attracted privateers and inventors like Horace L. Hunley. His team, originally operating out of Mobile, Alabama, realized that if they could not control the surface, they had to control the depths. The Hunley was not designed to win a fleet battle. It was designed as a psychological terror weapon. The strategic theory was that sinking even one major Union vessel from below would cause panic among the blockading fleet, forcing them to withdraw to deeper waters and reopening the supply lines. However, this urgency stripped the design process of necessary safety redundancies. In a modern naval context, a prototype undergoes years of uncrewed testing. The Hunley was rushed from blueprints to the water in mere months. It was a private venture, financed by investors looking for bounties on sunken Union ships, and adopted by a military command that had run out of options. The blockade had created a pressure cooker, where the risk to the crew was deemed acceptable collateral for the potential strategic reward. They weren't just building a submarine. They were building a desperate countermeasure to the industrial might of the North. To truly grasp the horror of serving aboard the H.L. Hunley, we have to strip away the outer plating and look inside the hull. From the outside, the vessel measured roughly 40 feet in length, constructed from 40-foot wrought iron boiler plates, riveted flush to reduce drag. But the interior dimensions reveal the true extremity of the design. The crew compartment was less than 4 feet wide and barely 5 feet high. For the 8 men inside, this wasn't just a vessel. It was a straitjacket. When we examine the propulsion system, we see the primary engineering constraint. Steam engines of the era relied on combustion, which consumes oxygen, impossible for a submerged vessel in the 1860s. Electric motors were decades away. The only available power source was human muscle. Running down the center of the ship was a massive, offset crankshaft. 7 men sat on a narrow wooden bench on the port side, bent over the shaft. Their job was to turn the crank in unison, a grueling physical motion that generated at maximum exertion, perhaps 3.5 to 4 knots of speed. This mechanical limitation is critical. To move the ship, the crew had to exert themselves heavily, consuming the limited air supply within the hull at an accelerated rate. The pilot, usually the commander, stood at the forward viewports. He controlled the diving planes and the rudder, but his most vital instrument was a simple candle. The candle served a dual purpose. It provided the only illumination in the pitch-black interior, and it acted as a primitive oxygen sensor. If the flame flickered and died, the crew knew they had only minutes before they suffocated. The ship's buoyancy control was equally primitive. Fore and aft, the Hunley was fitted with ballast tanks. To dive, the crew opened seacocks to flood the tanks. To surface, they had to manually operate hand pumps to force the water out. If these pumps failed, or if the crew became too exhausted to operate them, the submarine would simply settle to the bottom and remain there. There was no compressed air blow system, no emergency ballast drop. This was a machine with zero margin for error. But the most dangerous component of the Hunley was not its engine or its life support. It was its weapon. Early designs attempted to tow a floating explosive charge behind the sub, hoping to dive under a ship and drag the mine into it. But in testing, the tow line drifted, threatening to blow up the submarine itself. Confederate engineers pivoted to a spar torpedo system. They mounted a 22-foot-long iron pole, the spar, to the bow. At the tip sat a copper cylinder filled with 135 pounds of black powder. The design intent was for the Hunley to ram the enemy ship, driving the barbed point of the torpedo into the wooden hull. The submarine would then back away, and a trigger mechanism, likely a lanyard pulled as the sub retreated, would detonate the charge. From a modern engineering standpoint, the flaw here is terrifyingly obvious. A 22-foot standoff distance is negligible underwater. Water is an incompressible fluid. It transmits shock waves with far greater efficiency than air. By designing a weapon that required the delivery vehicle to be physically connected to the payload until moments before detonation, the engineers had essentially placed the Hunley inside the blast radius of its own weapon. They had built a delivery system that worked, but they hadn't calculated the physics of the delivery. It is the night of February 17th, 1864. The water temperature outside Charleston Harbor is near freezing. The sea is calm, glass-like, creating ideal conditions for a vessel that rides barely inches above the surface. Targeting the blockade is the USS Housatonic, a 1,200-ton steam sloop of war. She is a formidable wooden warship, mounting 23 guns, anchored roughly 5 miles offshore. Her crew is alert. Intelligence reports have warned of a fish boat attempting to break the line. But looking for a submarine in 1864 means straining your eyes against the darkness, searching for a silhouette that barely exists. At approximately 8:45 p.m., Officer of the deck John Crosby spots a ripple in the water about 100 yards off the starboard quarter. To his eye, it looks like a surfacing porpoise or a drifting log. He watches it. It is moving against the tide. This is the H.L. Hunley on its final approach. Inside the iron tube, the environment is hellish. Lieutenant George Dixon and his crew of 7 have been cranking for hours. The air is stale, thick with the smell of sweat and the burning candle. They are operating in a state of hypoxic fatigue, their muscles screaming, adrenaline the only thing keeping the crank turning. Crosby realizes the danger. He shouts the alarm. The Housatonic beats to quarters. The crew rushes to their battle stations, slipping the anchor chain to get the ship moving. But it is too late. The Hunley is too close. The heavy cannons of the Housatonic cannot depress low enough to hit the low-profile attacker. The Union sailors rush to the rails with muskets and revolvers, pouring small arms fire into the water, bullets pinging harmlessly off the Hunley's curved iron plating. Dixon holds his course. He drives the submarine hard toward the starboard side of the sloop, just forward of the mizzenmast. The speed is agonizingly slow. perhaps 3 knots, but the momentum is sufficient. The 22-foot spar strikes the wooden hull of the Housatonic. The barbed lance at the tip of the torpedo bites deep into the oak planks, well below the waterline. The connection is made. Now, the critical mechanical sequence begins. Dixon orders the crew to reverse the crank. The Hunley begins to back away. As the submarine retreats, a lanyard connecting the sub to the torpedo trigger pulls taut. At 8:47 p.m., a massive explosion erupts. The 135 pounds of black powder detonates instantly. The blast blows the entire stern off the Housatonic. A geyser of water and timber shoots into the night sky. The Union ship is mortally wounded. The sea rushes into her hull with terrifying speed. Within 5 minutes, the USS Housatonic slips beneath the surface, becoming the first ship in history to be sunk by a submarine. But what happens to the Hunley? According to witness testimony from the surviving Union sailors clinging to the rigging of their sunken ship, a blue light was seen on the surface shortly after the explosion, a prearranged signal from Dixon to the shore battery on Sullivan's Island, indicating success. Mission accomplished, returning to base. However, the Hunley never returns. Forensic reconstruction of the timeline reveals a haunting anomaly. The submarine does not struggle back to port. It does not drift aimlessly for days. Instead, mere minutes after the detonation, the H.L. Hunley settles gently to the ocean floor, resting on a layer of silt just 1,000 feet from its victim. There is no panic inside. When the wreck was recovered, the scene inside was frozen in time. The crew was found still seated at their stations. No one had released the emergency weights to surface. No one had attempted to open the hatches. No one had even moved from the crank. They simply sat there as the submarine filled with water and became their tomb. For over a century, this tableau baffled investigators. Why did a crew that had just achieved the greatest naval victory of the war simply sit down and die? The answer lies not in what the explosion did to the enemy ship, but in the invisible physics of what it did to the water itself. For decades, the prevailing theory was that the Hunley had been swamped by the wake of the sinking Housatonic, or perhaps damaged by a lucky musket shot that cracked a viewing port. But the recovery of the submarine in 2000 changed everything. The hull was intact. The bilge pumps were unset. The airlock was sealed. The skeletons were found sitting at the crank, suspended in time. This lack of panic evidence led modern forensic engineers to a chilling conclusion, confirmed by blast propagation simulations conducted at Duke University. The culprit wasn't water, it was the shockwave. When 135 pounds of black powder detonated, it created a massive pressure wave. In the air, a shockwave dissipates relatively quickly, but water is incompressible. It transmits pressure with lethal efficiency. The Hunley was less than 20 feet from the epicenter of the blast. Crucially, the iron hull of the submarine did not shield the crew. Because the acoustic impedance of the iron was closer to that of water than air, the shockwave passed right through the metal skin of the ship, barely losing energy. It then hit the only compressible objects inside the vessel, the air-filled lungs of the crew. The physics here are brutal. The shockwave compressed the air inside their chests instantly, rupturing the delicate alveolith air sacs responsible for oxygen exchange. This trauma, known as blast lung, would have caused immediate, massive internal hemorrhaging. The crew likely didn't even hear the explosion before the physics of it killed them. They were instantly incapacitated, perhaps knocked unconscious, or killed outright by the sheer concussive force. They didn't drown. They didn't suffocate. They were simply turned off. The Hunley drifted on its remaining momentum, slowly filling with water as seals failed or the tide rolled it, becoming a coffin for a crew that was dead before they hit the bottom. The tragic flaw of the H.L. Hunley was not mechanical, but conceptual. The engineers had solved the problem of underwater propulsion, but they had failed to account for the lethality of underwater ballistics. By mounting a contact mine on a short spar, they had essentially built a manned suicide bomb. The weapon worked perfectly, but the delivery system ensured that the attackers would share the fate of their target. The Hunley proved that a submarine could sink a warship, ending the era of invincible wooden fleets and changing naval doctrine forever. But it also proved that until the invention of the self-propelled torpedo, which would allow a submarine to strike from a distance, the concept was practically suicidal. In the quiet darkness of the conservation tank where the Hunley now rests, we are left with a haunting testament to the cost of innovation. It is a monument to 8 men who cranked a terrifying machine into history, unaware that their engineering had already determined their fate. They conquered the surface, but they could not conquer the physics of the deep.